Swayam Prabha. Digital India. Educated India.
Hi, so welcome back. We've been now looking at the boundary layers, and we were at the viscous sublayer, right, in the last class, and we were looking at some mathematical relationships which will be applicable only to that region, right. So we started out like that, and we said that this we define some near wall region parameters or variables, so to speak, so which were like u tau, delta v, the friction Reynolds number, viscous length scale, friction velocity, right, the distance from the wall measured in viscous length, but basically y in terms of delta v, right, which is the viscous length scale. And that was y plus, right. So then we said something about the law of the wall, which is by Prandtl in 1925, which basically says that a Reynolds number which is close to, at a very high Reynolds number or close to the wall, there is an inner layer in which the velocity profile is determined by the viscous scales independent of the boundary layer thickness and the free stream velocity. Right, and so therefore we we said we define these lengths, the viscous wall region, outer layer, viscous sublayer. So then we came to the viscous sublayer, and we started looking at some things, some relationships which will be valid there. Okay, so we came up with that, and we found that in the viscous sublayer, essentially the u plus, the velocity in the velocity there, which is a function of the y plus, right, is actually equal to the y plus. This is a linear relationship, right, and du dy dash is actually equal to 1. Okay, we did this the last class, and that's where we stopped. Okay, what we'll do now, and this was just a minute. This was it's basically. This is essentially the law of the wall, right? Okay, so now what we will talk about, however, is the log law. Okay, let's do that. Okay, we'll talk about that now. So first I'm going to define some length scales that we're talking about. So inner layer, right, this essentially means that at high Reynolds number, okay, okay. Now at high Reynolds number, the length scale, right, is 0.1 or 1/10 of delta by delta v, and this delta by delta v, right, that's actually equal to the viscous Reynolds number, right, Reynolds number in the viscous length scale. So this is, okay, let's just say, or y plus is equal to 0.1 Re. Well, 0.1 Re, right, and y plus is much larger than 1. So this is a length scale we are talking about, where y by delta, right, y by delta is less than 0.1, and y plus is, which is delta by delta v, right? So sorry, I mean y plus is y by delta v, that is much larger than 1. Okay. So essentially the y is much larger than delta v, but the y is much less than boundary thickness. Okay. All right. So now once we know that, now then when y plus is very large, right? So at well, I don't have to write that actually. So I have written it here, okay, that it's very large. So at large y plus, right? Now what this means, right? What this means actually, if y plus is very large, is that negligible. Okay. Okay. So yeah, that makes sense, right? Because we said that the smaller, at very small length scales, is that's where there is viscous dissipation, right? So viscosity dominates in those regions. So therefore, if y plus is very large, then the effect of viscosity is negligible. Yeah, right. So in that case, then this function which we have is a non-dimensional function which we've defined earlier. Let me just go back to that and remind you. Okay, so this phi that we had, yeah. So this is the phi that I'm talking about now. This phi. Okay. So we defined the velocity gradient. I mean the mean gradient of the mean velocity in this fashion, right? So these are all the viscous length scales that we're talking about. Okay, so y by delta v is nothing but y plus, right? Okay. So if that is negligible, right? Now just look at this. Now phi right. So which is actually right, but if the viscosity is negligible, right, then this also means, or this also means dependence of this length scale, the viscous length scale, right, on the nu also negligible, right? Make sense? So the length scale is such, I'm operating at such a length scale. When I say length scale, what I basically mean is that if you would sort of have a boundary layer, right? So this is sort of the distance which I'm going away from the solid surface over which the boundary has formed. So it's the flat plate boundary layer, right? So I'm going away farther from that. So in that the effect of viscosity is negligible, which essentially means that the viscous length scales delta v, their dependence on the velocity on the viscosity is also negligible. So this means that this kind of, if that is so, right, so then this will kind of become stable, which means that this is kind of gearing towards being a constant, because the change is negligible, right? So because every time you change because if the dependence on the viscosity, right, that depends on Reynolds number also, right, and the length. So if that is negligible, then even if if you change that delta v within this range of length scale that we're talking about, there is not much change, right, because it is not dependent on viscosity, and viscosity effects are not dominant in this length scale, right. So this essentially means that this is gearing towards becoming a constant. Okay. Now, that gives me some idea, all right. If that is so, okay, let us just say that this constant is 1 by k. Okay. So, we are going to just say that. So, what you can say is that just that, right. So, this is something, now again this is something you can basically say only for this, I mean length scale obviously. Okay. It could take on a form like this, right. Now, let us integrate this, okay, or let us go to the next page and do that. Okay. So, I said is constant, which is equal to 1 plus 1 by k say, okay. That is a constant. Okay. So, then mean velocity gradient, right, then we integrate. Okay. Now, if I integrate this, so if I integrate, so essentially u plus is equal to 1 by k plus another integration constant, right. This is another integration constant. Okay. So, essentially this is the, so if you see this in the length scale that we have just, I have just shown you, right. So, u plus, right. So, there is a relationship between, u plus and y plus, and what is the relationship? It's a log relationship, right, and this is essentially the log law. Okay. This is the log law. So, this is the log law. Okay. K is the von Karman constant. Okay. And what could be the values of these? Now, this is what could be the value. I mean, you have to, I guess, experimentally, do several experiments and sort of find out. So, it depends on, how you set it up. So, more or less throughout literature, you will find that these values are within 0.05 plus minus 0.5, like throughout literature. So, from literature, right, we get these values to be within plus minus 0.5, right, of k is this and b is 5.2. Okay. So, if I just go back to what we did earlier, okay. So, this is what I used just now, okay. Just wanted to bring this up. So, this del u star, del u plus dy, this is something I used just now. Okay. We define this, right, and then u plus is this, right, which is mean velocity in terms of the viscous scale velocity, and so du plus dy is this. This is something I used just now. Okay. which is this, right? So it is essentially 1 by this into phi, but then the phi is a constant, so I write that as 1 by k. Okay, and then I integrate and I get this. Okay, so now what we basically said, therefore, so in the viscous sublayer also we found out a relationship, right? And that relationship basically between, say, you, so let's just say that what is it that I am, what is the relationship that I'm developing? Well, the distance from the, from, this is a distance that I am measuring in this very close to the wall, right? And that is something that I'm representing as y plus, right, in terms of the viscous length scale. So this y plus, if I come very close to the wall and at high Reynolds numbers, what I find is that there's a relationship between u plus and y plus, which is basically linear relationship. Now this is in the viscous sublayer, right? And du plus dy plus is equal to 0. So this is something we had done for the viscous sublayer, and now coming here, this is for the log law, and this is the region where, so this is the region that it is, we define where y by delta is less than 1 and y plus is much more than 1. So this is something that this is the length scale that we are working at. And in this length scale, we find another relationship, right, between, so here we find the relationship between u plus and y plus, which is essentially the log law, right, and we also have the values of B. So given any sort of a turbulent flow field at high Reynolds number from boundary layer, so if there is this region, the bounds which are given here, so in that this log law is applicable, right, and du plus dy is essentially inverse of y plus, right. So that's interesting, right. So y plus, if you, well, y plus, the more it decreases, you see du plus dy will become larger, which is what it's supposed to do. And the more you go away from the walls, which is like y plus is very large, du plus dy is going to become, almost negligible, right? Okay, so that is that. Okay, now. Just to say one thing before I sort of almost sum this up, okay. So then essentially what we are saying is, to almost in summation here, that you have a viscous sublayer, right, you have a viscous sublayer, right, which is y plus less than 5. We've talked about this before, and then you have the viscous sublayer where you have the law of the wall. Yeah, the law of the wall. Yeah, the wall law, and then the Prandtl's law of the wall law, and then you have the log law region. Okay, so this is the log law region, which is essentially y plus is, say, greater than 30. Okay, so between these, right, between this, okay, is a buffer layer. Okay, this is a buffer layer. So transition between viscosity dominated and turbulent dominated. Yeah, so essentially I think I've been repeating myself quite all the time, I think. So in the sense that viscous sublayer is much closer to the wall, the log law region is a little farther away from it. Now the point is, so viscous sublayer, of course, it is viscosity dominated, and the log law region, the viscous effects are negligible, so it is more of, say, turbulence dominated. Now this, however, this transition between this viscous dominated and the turbulence dominated, obviously it's not like a sharp change or anything. It happens over a region, which is essentially the buffer layer that I'm writing out here. Okay, all right. So now I'm going to kind of sum this up. All right, I'm going to sum this up, and we've been discussing the length scales and what we learned from this whole exercise. I think it will be nice to kind of sum this up and understand that there are just so many length scales involved, and each is different. Each has its own characteristics. And now we've also been able to find out a few relationships which are valid for those two particular, length scales, which is interesting, right? It's the same boundary layer, and now you throw in turbulence, and you see that things get really sort of mixed up. Okay, so let me like I said, let me make a gist of it. Okay, now this is the say region. Okay, and let's just say okay, now you have the inner layer, okay, such that let me okay, fine, let me just write that. Now here of course the mean velocity, right, is determined by the length scales which we it's the inner layer, right. So here these are length scales which are independent of the boundary layer thickness and free stream velocity. So we defined separate length scales in here, right, viscous length scales, and which is where this is coming in. So in here the mean velocity is determined by u tau and y plus, right. So which is independent of free stream and boundary layer thickness. This is something that we said earlier, right? Okay, that's the inner layer. Then we have the viscous wall region, right? We have the viscous wall region, which is okay. So y plus is less than 50, or rather y is 50, within 50 times of the viscous length scale, delta V. Okay. Now shear stress is primarily due to viscosity. Okay, in here, as you can see, now shear stress primarily so is viscosity dominated, right, viscous wall region, that's what we're saying. Then this is interesting. This is a viscous sublayer, right, where this is this. This is where the law of the wall is something that we developed, right. So interesting. So shear stress is primarily due to viscosity. You come even further down, and the further closer to the wall, which is the viscous sublayer, right. Here it's very interesting that yes, of course, the shear stress primarily due to viscosity, and what is interesting is that the Reynolds stress becomes negligible, and this is something we sort of right. Reynolds stress is negligible, well, compared to the viscous stress, I guess. Well, yeah. So that's interesting. So It is primarily due to viscosity, okay, and you come close to the, so definitively when you're in the viscous sublayer, the Reynolds stress is gone. Now think about this. Now what does this do to your numerical equation? Well, I mean, this is a huge term, this Reynolds stress term, right? And that is the source of a lot of computational difficulty. So in the viscous sublayer, however, you can take that out because that's negligible compared to the viscous stress, right? So that's the advantage. This is how kind of we, Okay, so outer layer, then we come to the outer layer, which is okay. Yeah, so here basically viscosity effects are minimal. So here essentially direct effect of viscosity is negligible. Okay. Then, well, now let's just talk about that. Then we have the overlap region. So there will be some, right? So we said y plus is greater than 50, right? And y by delta is less than 0.1. So this is the overlap region. This is 50, and y by delta is less than 0.1. Okay. So this is essentially the region of overlap between the inner and outer lengths at high RE. That's all, right? So let's just say this is the inner layer. Yeah, well, this is the outer layer. This is the overlap region. Okay, so this one is essentially well, this is the region of overlap between inner and outer regions, outer layers. At high RE. Then again we have, of course, the log law region, which we said where yeah, so y plus is greater than 30 and y by delta or did I say 0.1 in the last slide? What did I say? Yeah, so I said inner layer. I think we should sort of stick by that. Why are we doing that? Yeah, I think it should be 0.1. We should stick to that, right? Inner layer, essentially. Let's stick to that. Okay. So this is the log law region, and we worked it out that the log law will hold here. Okay, and here again viscosity effects are negligible, right? So well, viscosity effects negligible, right? And log law right? Now this log law is essentially connecting the velocity with the length scale, you know. So essentially u plus is a function of y plus, right? And this is a basically a log function, right? This is the log function. Let's just put it that way. So yeah, so that's exactly what we're trying to say, right? So this is my. So when I say this is a a logarithmic function on the right hand side. Okay, that, and so log law will hold. Okay, and I think we should also, so viscous sublayer, this is where the law of the wall will hold. So here law of the wall will hold. This is Prandtl's 1925, proposed by him, and essentially linear relationship so u plus is equal to y plus. Okay, that's that. And finally, let us write down the buffer layer. So again, we have the buffer layer such that between 5, right, which is the viscous sublayer, and 30. Okay, yeah, 30. This is the one, the log law region. Okay, so viscous sublayer is where viscosity is dominated, and when y plus is greater than 30, you have the log law region where turbulence properties and more turbulence is dominating and viscosity is not. So this viscosity not dominating and dominating, so that is happening over a buffer layer, which is this. Okay. Yeah, so I think this the way I would write this is overlap region, or I think the way I would write this is region over which transition from viscous dominated to turbulence dominated flow happens. That's how I would write it. It's making sense to me that now I'm going to transition slowly my flow in such a way that viscosity is not going to dominate and turbulence will dominate, and that's not going to happen like that. So it's over a region, and that is that buffer layer. Okay. All right. Now let's do this. Now this needs some artwork for. So I'm going to sort of draw this up and do this. Okay. Now excuse me, because I will need to draw some really long straight lines, and that might become okay. Let me try that. Okay, why not? Maybe that's a good idea. Okay. I think if I draw that and if I give it, it's going to draw me a line or what? Yeah, that's cool. Okay, that's a nice thing. All right. Okay. Now, what I'm going to do here, okay, so let's just mark this, okay? Now this, I say 10 to the power minus 4. So I've given you a lot of this, y plus is this and that and all of that, right? So we'd like to get some numbers right, isn't it? So those numbers are very important. Now 10 to the power minus 4, then let's say this is 10 to the power minus 3, then we'll say 0.01, 0.1, say 0.3, 1. Okay, yeah, I think that's fine. So essentially this is y by delta, right? This is y by delta. Now okay, that's another line. Okay, and here, so this is 1. Okay, so this is 5, then this is 10. Okay, this is say 30, this is 50. Okay. Okay, let's just say this is 10 and this is 100. Okay, so let's just say this is this is 30 and this is 50. Okay, this is 1000 and 1 is 10,000. So this is y plus. Okay, so let's just do something here. Okay, so I'm basically trying to draw a grid here. You can see that. Okay, okay, okay. All right, let's sort of do that. Okay. Okay, so okay, let's just say that's 100. That's the point we're looking at. Okay, just excuse me. All right, okay, not bad. So this is the 10. Okay, I can overwrite it. All right. So this is the point that I'm looking at. Okay. All right. Now I'm going to basically write out the scales. That's all. Okay. So now the all these length scales that we just said, this is just sort of putting a gist onto that. Okay. So let's just say, so then now again I'm going to draw some lines and we're going to do this. Okay. So so you have an outer layer where y plus is basically greater than 50. Okay, so this is my 50 here, so which means, okay, let me first draw that. So this is, yeah, okay, all right, so that's 50, and so I have an outer layer, right? Okay, right, this is an outer layer. Okay, and I'm going to say outer layer, right, y plus is greater than 50, right. Then we have an inner layer, right, where y by delta is less than 0.1. Okay. So we have an inner layer, okay. So an inner layer This is the inner layer. Right, where y by delta is less than 0.1. Okay, see if that, so this is the one, so y by delta is less than 1. Okay, so this is what I'm looking at. Okay, now so we have the outer layer, we have the inner layer. Okay, now then you have a viscous wall region. Let's do that first. Viscous wall region is y plus is less than 50. Okay, so right there. Okay. Okay, and this is the viscous wall region. Right, where y plus is less than 50. Yeah, okay. Then you have a viscous sublayer, right, which is y plus is less than 5. Okay, then so yeah, okay. Then you have a viscous sublayer, which is y plus is less than 5. Okay, so which is this. Okay, so this is the viscous sublayer, right, y plus is less than 5. Yeah. Okay, so then between the well, you know, between the viscous sublayer, right, and the inner layer, right, so you can see that now. So there is an overlap region, is it? Is there? Yeah. Well, viscous sublayer, and there's a certain buffer layer. Okay, so y plus is greater than 5, okay, and less than 30. Okay, okay, I haven't drawn anything. Let me first do that. Okay, so this is the 30 bit. Okay, let's see. So then we have the log law region. Yeah, that the buffer is between the two. Okay. Now the log law region, the log law region is basically y plus greater than 30. Okay, here, and y by delta less than 0.3. So which is here. Okay, so log law region is this. Yeah, so okay, so this is the log law region, right, where y plus is less than, well, yeah, 0.3, you could make that as 0.1. You know, I think I said that, I wrote that. Yeah, so we could, you know, we could basically say the log region is not up to 0.3, should be to 0.1. We could do that. So y by delta actually. So y plus is actually greater than delta. So let's just where y plus is greater than 30 and y by delta is less than 0.3. Well, we could do that, or we could basically say that no, it's up till here. Yeah, well, we could do that. Okay, so now if you see here, so you have a viscous wall region, right? And so you have a log, where was the log? Yeah, log law region, right? And you have a viscous wall region as well. So, you can see that from the viscous sublayer, which is right down here, okay. So the viscous sublayer is where viscosity dominates, log law region, viscosity does not dominate, turbulence dominates, right. So you go from this, the viscous sublayer, right, to the log law region, and this is a buffer region, right. So this is that buffer layer which is basically between 5 and 30. So you see there is a viscous sublayer, so viscosity is dominant, right, and then this log law region starts where viscosity is not dominant, the dominance decreases. So the moment you cross this, the dominance starts decreasing. So therefore this is the region in between, right, which is the buffer layer. Okay, let me just write that. Okay. Well, I think I can use the same color. So now this one is essentially that. So this to this is the buffer layer, right? This is the buffer layer between viscosity dominated and turbulence dominated region. Actually, I wouldn't put it that way. When the domination of viscosity decreases and turbulence comes into play. Okay, so that's the buffer layer. Okay. Then we also have the overlap region, right, which is greater than 50 and less than 0.1. Okay, so that's basically, now this buffer layer is between the transition. Okay, so I'm going to write something here. So this is like transition from new, right, yeah, viscosity dominant to viscosity becoming negligible, right. And then between the outer layers, between the outer layer and the inner layer also there is this overlap region, right. So overlap region, if I look at this, it's somewhere between 50, yeah, 50 to 0.1, right, 50 to 0.1. So that's the overlap region. Okay, so this is the overlap region. Okay. So this again is the overlap region. So y plus is greater than 50 and y by delta is less than 0.1. Okay, I think we are done, isn't it? Yeah, I think we sort of put everything down together. Okay. Yeah, so I think we got that, got everything. So we got, wait, let me see, checking the 6, 1, 2, 3, 4, 5, 6. Okay. So I think that's it really. Okay. So this is something that we're talking about in terms of a boundary layer, and it is interesting, right? So you have an outer layer, right, and then you come to this region where there is a log law, region. This is the outer layer. So y plus is greater than 50. And then you come, which is the log law region, right, and then is a buffer layer, transition from this. So log law region, and then you slowly back away from the dependence. The viscosity effects slowly start dominating as you go closer to the wall, which is kind of happening the way I've written this. So vertically, if I'm coming down, I'm actually almost saying that the way I've drawn this chart here, so actually it would seem like if I'm coming from to the top to the bottom, so it's like you're actually y by delta is happening. Okay, actually I'm getting closer to the wall because the viscous sublayer is right here. Okay, so then you have a buffer layer, there is an overlap region, right? Then there's an inner layer, then the viscous wall region, and then of course the viscous sublayer, which is y plus is 5. Okay, so I think that kind of really takes care of that. Okay, so I mean we could do a small exercise. How does this help? Now, I mean, in what way is this useful to us? Okay. Well, I mean, in what way it is useful to us? Okay. Okay, right. Now let's just say I'll just make a small calculation here. Just a sample. I mean, what we could be looking for. Okay. Now, for example, let's just say that a Reynolds number, right, which is equal to this is equal to 10 to the power 4. Okay. Now, y plus is equal to y by delta v. Okay, y by delta v. Therefore, y plus is equal to 1 by 10 to the power 4 of y by delta. Okay. So for a for a given boundary layer thickness, right, and at the given Reynolds number, viscous length scales, and for the y that you're looking at, you should be able to find out. So for the given y, how do I calculate the y plus? So at what region am I located? What is my y plus? On the scale I can figure out. So y by delta. So in the sense that now if I look at this chart here, so y by delta has several values. So what if y by delta is equal to 1, right? If y by delta is equal to 1, then this thing, then say y by delta is equal to 1, right? Which will be here, y by delta, right? So this means that y plus is equal to 0.1, right? So I guess that it is very, very, very small. Okay. Instead, if I said that this is equal to y by delta, right? Y by delta is equal to or rather, if I were to do the opposite, what if I did say y plus? Okay, so that's how it works. Now, if I say y plus is equal to, so y plus is equal to say 1,000. Okay, so y plus is 1,000, 10 to the power 3. Okay. Yeah. Well, actually, I made a mistake here. Okay. Let's just put that down. Y by delta. This doesn't make sense. Okay. So that is 10 to the power 4 into y by delta. Is that right? So now say y by delta is equal to 1, which is actually right here. Okay. If that is the case, then this is y plus is actually equal to 10,000, right? Which is, I'm here. Okay. So I'm in the outer layer really. Okay. So what if y by delta is equal to say 0.1? Okay. So say y by delta is equal to, or say 10 to the power minus 3, right? So this means that y plus is actually equal to 10 to the power 4 into 10 to the power minus 3, which is equal to 10, basically. Okay, so it's kind of in the buffer layer, actually, you know. So it's here, right here, you know, because if it is 10, right? So in a sense, for a given Reynolds number, right, we can figure out the length scales. We can figure out the length scales so that we will know where we can apply the log law, where exactly the viscous sublayer is located, and so on and so forth. Okay, so that's how these length scales, which we've described for, you know, using the law of the wall as well as the log law, will be useful. Okay, so I think I'll stop now, and we'll take up something new in the next class. Okay, thank you.